Hello, welcome back. So, in this lecture we shall be looking at some of the steps in Vlsi physical design automation that we shall be discussing in more detail in the modules to follow. So, the lecture is titled Vlsi physical design automation part 1. So, here if you look at the main steps in the Vlsi physical design cycle, so here I have listed some. In fact, these are specifically the steps which I shall be discussing in this course in significant detail. So, again I repeat, whenever I talk about Vlsi physical design, I assume that I already have a circuit netlist available with me. Typically, it is a transistor level netlist. It can also be a gate level netlist, which can be technology mapped to standard cell libraries. Okay. So, I assume that that kind of a netlist is already available to me. Then I go through some sequence of physical design automation steps in order to create the final layout. So, the main steps are partitioning and floor planning, followed by placement, then the very important step of routing, then static timing analysis, signal integrity crosstalk issues, clock and power timing design, and finally physical verification and design sign off when we are ready to send our final design to the fabrication facility for the ultimate manufacturing of the device or the chip. Okay. So, let us start with the first step, floor planning. Floor planning, what does it mean? A number of circuit blocks have to be laid out on the silicon floor. Determine the rough position of each of the blocks, determine the shapes, determine the pin locations. You see, I have mentioned a lot of things. Let us talk about an analogy, you will be able to appreciate better. Suppose you are building a house from scratch. It is not that a flat you are buying which someone else has constructed. So, you have a floor area, you want to create your floor plan and you want to create your own design with respect to the rooms, spacing and so on. You see, what are the different steps? Let me just carry an analogy. So, in floor planning, you have a number of circuit blocks that have to be placed, but here let us say you are going for a say a 2 BHK house, a floor. Here your blocks will be 2 bedrooms, let us say 2 toilets, 1 drawing cum dining room, 1 kitchen and 1 balcony. These will be your blocks you want to place, let us say, right. Now, you have an idea regarding the approximate size of these blocks, because you know how big your 2 bedrooms should be, how big the drawing room should be, but the exact shape and configuration is not yet decided. That you can plan along with the other blocks when you are placing them. Like for example, the drawing room, should it be a square like, should it be a little rectangular shape, should it be L shaped and so on. So, the exact shapes of these blocks will have to be decided during this phase. Not only that, in Vlsi floor planning I mentioned about the pin locations. Here in this analogy, the pin locations will correspond to the exact location of the doors and windows. So, where you want to put the doors, windows and the corridors if required for connecting the different blocks. So, there is a very similarity between these two problems. So, in Vlsi we look at a similar kind of a thing. I have different blocks, I have a fixed area of silicon where I have to place everything. I have to tentatively find out or fix where to place this, and if the blocks are flexible I can adjust their sizes Like for example, if I have a block, let us say, whose area I know is 10 units by 10 units, but its layout is not fixed. So, I can lay them out in so many different ways. I know that the total area is 100 square units. So, I can lay it out like this, I can lay it out 20 by 5, I can lay it out 5 by 20, I can lay it out 25 by 4. So, there are so many options available to me, right. So, during floor planning you will have to exercise these options and find out which of these will give you the best kind of solution. Now, this is of course a mandatory step for full custom design. Now, again here we are coming to the design style related issues. You think of the semi custom or standard cell based designs where all the cells are placed in rows. So, now my placement problem is not unrestricted, it is not that I can place anything anywhere. A block or a cell I have to place only in one of the rows. Okay. So, the floor planning problem per se does not exist in standard cell designs. For FPGA gate array it does not for FPGA floor planning does not exist. You have to place a circuit module into one of the CLBs, only placement is there, but floor planning you need not have to do there. But of course, sometimes you can use some bit of floor planning there, because you may want some circuit portion to be allocated to one part of the FPGA in order that the delays, interconnection delays are less. There are ways to interconnect with the FPGA software to force that certain blocks must be mapped to the CLBs which are located in a close neighborhood within a rectangular region, those you can specify. Okay. Fine. Now, before floor planning or along with floor planning, there is another step called partitioning which are carried out. You see, partitioning are carried out for various different reasons. Before I explain this slide, let me just tell you. Suppose I have a very big design and I have a particular technology using which I can manufacture a chip. Let us say, for example, I am capable of fabricating 1,000,000 gates in the chip, but I see that in my design there are 2.5 million chips. So, what I know is that I have to break my design into 3 chips, that is what I need. In one chip I cannot put. So, how to partition my whole design into 3, you can say, partitions, such that each of the partition size will be less than 1,000,000, and of course, another very desirable thing is that the number of connections between the partition should be minimized, because I would not like a scenario where I need 1000 connections to be made between 2 chips, because whenever you go off chip the delays increase by an order of magnitude. So, I would like most of the interconnections will be inside the chip, only few connections will go between the chips, right. Similarly, here I have an example where you can see that there is a gate level netlist here. So, there are 48 gates. Suppose I want to divide it up into 3 partitions. The diagram below shows a good partition, where you can see the 3 partitions in different shades, where you see that the sizes of the partitions are approximately equal in size, 15, 16 and 17. And also you look at the number of interconnection wires between the partitions. Between first and second partition there are 4 connections, So, we say that this cut size is 4. Similarly, between second and third there are 4 connections, this cut size is also 4. First and third there are none. So, we can say that this is a good partition. So, this partitioning can be done at any level. I talked about at a very high level where in terms of chips you can do it, you can do it in any level in fact. Okay. So, this partitioning is an important step before you go for means placement or floor planning typically. Okay. Now, let us come to a floor plan. Now, in this diagram here we show the representation of a floor plan, how a floor plan is represented. Like on the diagram here in the left, you see 1, 2, 3, 4, 5, 6, 7, 8, these represent 5 modules or blocks. Their areas roughly indicate their sizes, right. Now, this is the rough floor plan that I have arrived at. Well, in terms of the house again I can say this 4 will be my drawing room, this 7 and this 2 will be my say bedrooms, like that. This one can be my kitchen and so on. So, once I have a floor plan like this, how do I represent it? Because in a typical VLSI circuit, I am talking about a situation where there are thousands and thousands of such blocks, maybe more. So, how to handle them, how to represent them efficiently, so that I can carry out some manipulation, I can arrive at a good or efficient floor plan. Okay. So, here we show one possible ways of representing a floor plan in terms of a tree. This tree represents a cut. See, here you can see that the nodes are marked either as plus or as star. So, what I mean is that this plus means a horizontal cut, and a star means a vertical cut. Well, what does this mean? Suppose I have a floor plan where I have 2 blocks A and B placed side by side, separated by a vertical partition. So, this I represent as follows. Similarly, if I have a scenario where 2 blocks say C and D are represented by a horizontal partition, I represent it as this. Well, let us take another example, a slightly composite one. Let us say I have this. So, the way I represent it is that first I use this vertical cut. So, star. So, on one side it is A and the other side is this whole thing. This whole thing again has a horizontal cut. So, plus B and C. So, this is one way of representing a floor plan. So, let us now come to this example once more. In this example, this is one possible tree representation because it is not unique. Like starting from the lower level, 3 and 6 are connected by a vertical line, by a horizontal line. So, 3 6, 3 6 together is connected to 1 by a horizontal line. So, again a plus 3 6 and 1. 2 5 are connected by a vertical line, 2 star 5. Then this and 4 are connected by a horizontal line with a plus 4, and this whole thing and this whole thing are connected by a vertical line. So, again a star, this and this. on the other side 8 and 7 by horizontal line, and this again with a vertical line, right. Now, this is a tree, this is a graphical representation. Now, for those who have studied computer science data structure, you will know that any such tree, this is a binary tree with some operators in the vertex nodes and some modules in this case in the leaf nodes. This can be represented in the so called Polish postfix notation. So, what is Polish postfix notation? You see this one, this A, B and star, this I represent as first the two leaf nodes, then the operator on top A, B star. I write it like this. This I write as C, D plus. This one I write as, first this one will go B, C plus, I first do this, then A and this, then A, this whole thing star. This is how Polish postfix notations are written, and this is a unique notation, this does not need any parenthesis or brackets. So, you know that any operator if you encounter, you operate it on the previous two operands. So, plus will work on B and C, you get something, star will work on A and this, so you get this whole thing. So, step by step you can go, right. So, here you can also see this, you have done exactly the same thing. 3 6 plus means this one, 3 6 plus, 1 plus, that means 3 6 plus and 1 plus, 3 6 plus and 1 plus, 2 5 star, 2 5 star is this, then 4 plus, with that 4 is plus, and this whole thing and this whole thing there is a star, this 8 7 plus, 8 7 plus, this whole thing and this 8 7 plus is star. So, like that it proceeds. So, here you can work out, this is actually called postfix notation. So, a floor plan can be represented as a postfix notation provided it is sliceable. You can slice it into horizontal and vertical lines like this, but we shall see later when you discuss in detail that there are certain floor plans which cannot be represented in this notation, like I am showing an example. Suppose there are 5 blocks A, B, C, D, E, but there is no continuous horizontal or vertical lines that can slice this floor plan. So, here you cannot use plus, you cannot use star, this cannot be represented like that. So, we shall see later how to handle this kind of floor plans, right. Okay. So, after floor planning, the topic that we shall be discussing is called placement. See, during floor planning, we have already fixed the approximate locations of the blocks. Like we have said, so again with respect to the design of a flat, I said that here I have my first room, here the second room, here the dining space and so on. I have tentatively fixed the locations, but the next question comes, well, how do people move from this room to that room? So, for that possibly I will need some additional corridors or places to walk and reach there, approach. So, with respect to Vlsi design, I need some additional space through which I can interconnect the blocks. The so called routing areas are required. Okay. So, the placement problem says, given a set of blocks with defined shapes and pin locations, determine the position of the layouts. Not only that, you keep adequate space between the blocks to run the interconnections. So, here your interconnection modeling and cost estimation are important, because you see the exact interconnection you will be doing later during routing, but now you are trying to keep some space and place the blocks in an optimum way such that your expected cost is minimized. Okay. So, you have to use some simple estimation of routing cost, so that you can evaluate and compare between two alternate placement solutions. You can say that, well, this is more expensive than the other, so you take this. Okay. Fine. And as I said, for some design styles like FPGA and semi-custom standard cell based, floor planning and placement problems are identical, they are not different, but for full custom they have to be done separately. So, let us look at the standard cell scenario once more. A standard cell chip floor plan will look like this, with the IO pins, the IO cells on the boundaries, and the rows will be the standard cells with routing channels in between. So, now my placement problem will be here, as I mentioned again earlier, how to place a cell into one of the rows. And once you have placed the cells, you can estimate the routing channel cost and you can keep adequate space for that. You see, for standard cell the problem is not difficult. If you see later on that your space is a little less, you can move the entire row a little up or down. Okay? So, you can do it later, those adjustments you can do later, but for a general, say, means a full custom thing where there are so many blocks, moving a block around is not so easy, because moving a block to make space here might make the space on the other side less, that can create a problem, right. So, this is one, and again here if you can see that I have shown two standard cell placements. This is a so called bad placement and this is a so called good placement. See, the interconnections here are shown by straight lines just to see how complex the connections are. So, in the first case you see that there are lot of zigzag lines, large number, but in the second case you will see that the lines are mostly local, confined to the channels, and only a few connections are across channels. So, this is a good placement. Okay. So, the importance of placement is quite clear, that if I have a good placement, I can have the routing problem much easier later on, and also I can come or I can arrive at a final design which will be more efficient in terms of performance, because today interconnection area and interconnection delays are dominating the total performance of the circuits. So, if I can keep my interconnections simple and short, it will help in the long run. Okay. Okay. Once you have placed the blocks, now comes routing. So, once the blocks have been placed, you run the interconnection lines so as to complete all the connections or the netlists. Now, there are various categories of routings, grid routing, global routing, detailed routing, clock and power routing, etc., that we can talk about. And the thing is that a bad placement can make the routing problem very difficult, as I said. Grid routing means, grid routing is a problem which is quite general, which says that I have, let us say, let me show you diagrammatically. Say I have a layout area, this is my total silicon floor, and I have already some blocks which are placed, which means these are obstacles. I cannot run an interconnection through these blocks. Let us say like this. And suppose I have a problem where I want to connect a pin which is located here to a pin which is located, say, here. So, now my problem will be this grid routing says that how to complete this routing overcoming these obstacles. So, there are so many alternate paths. So, let us say this can be one alternate route. Now, once you have done this, now say I have another problem next, but I want to connect a pin here with a pin here. Now, obviously, since we have laid out this line on the same layer, you cannot follow the same route because there will be a cross. So, here possibly you will have to take a route like this. So, this is the problem of grid routing. There are obstacles, there are points or pins to be connected. Try to determine a path, typically means as short as possible, so that you can complete the interconnection, right. So, now in addition to this, there are global routing and detailed routing problems. So, I can give an example here. Suppose there are blocks out here, some pin locations are shown, they have to be connected in some way. The second diagram shows the result of global routing. Global routing, what it does is that it does not means it does not interconnect the pins in a precise way, but rather it tries to find out an approximate route. Like you say that these two pins have to be connected over this part, these two pins can use this part, this pin can be using this part. To connect these two pins, I can follow this part, because there can be other alternatives. For example, for this connection I could have used a path like this. So, it approximately tries to find out a path. This is global routing. Now, once a global routing is done, then each of these individual regions you consider one at a time and try to complete the exact wiring. So, here I am showing all the wirings on the same layer, but when we took that example of the channel routing, you recall I used two different colors to show the wires running on two different layers, one horizontal, one vertical. They can connect at certain points if required. Okay. So, this is global and detailed routing, roughly what it means. So, later on we shall be looking into these in much more detail, and we shall be working out a lot of examples. Of particular importance is clock routing. Now, you see, clock is a very important signal. There are many sequential circuit elements all throughout the chip, flip flops, registers, counters, they all require clock. And because typically clocks are edge triggered, many of the flip flops get triggered by their edges. If there is a variation in delay of the clock signal to one flip flop as compared to the other, then maybe one flip flop might get switched earlier than the other. So, in a circuit this might lead to incorrect operations. If all the flip flops that are supposed to switch together, there is a delay in the switching. Okay. So, there are many methods which have been proposed, which we shall be discussing to handle clock routing. Like one method I am showing here, this is called H tree, because you see every intermediate step looks like a H. So, the clock generator is in the middle, and all these points at the terminals of the H, these are the points from where clock signals are taken. Now, if you just measure, if you just see from the clock generator up to each of the terminal point, the length of the interconnection is the same, which means the delay of the clocks will be identical up to each of these points. But the trouble with this method is that in typical layouts, you do not have the clock locations so regularly placed, they will be haphazard and random often. You often do not get the opportunity to lay out this H type layout very neatly there. You see, you can have a layout where there are a lot of haphazard things. So, we shall see all these things later in the next lectures. So, I think we can just end today this lecture.